This is what we'll be talking about today. First, a little bit of a background on ANSYS Instruments, who we are, what we do. And then we will, for those of you who are not familiar, give a brief introduction to nanoscale IR spectroscopy and specifically AFM-based infrared spectroscopy. Kevin's going to talk about some major advances in AFM-based infrared spectroscopy, including one we're really excited about, fast spectra technology, and a new IR source with an extended tuning range, and also some expanded capabilities for complementary AFM measurements. And then I'll rejoin you in the second half of the talk, and we'll go over a variety of new publications and applications that we're really excited about. So with that, I'll turn things over to Kevin Kohler.
All right. Well, thank you, Craig. And I'd like to welcome all of you to this webinar. We'd certainly like to thank you for your participation in the webinar, and I will get started. So as Craig mentioned, we want to introduce a new NanoIR2 FS with fast spectra technology. This system has the new capability in terms of higher speed, resolution, AFM-IR measurements in seconds, and we'll be showing an example of that later in the presentation, as well as the incorporation of a new broadband source, which allows us to do resonance-enhanced AFM-IR in the high wave number range, or the short wavelength range. And then also for all of our products, we have some new AFM capabilities in terms of application modules, which we'll discuss. So the fast spectra technology is something where we have taken our previous capability using the quantum cascade laser, and we've increased the speed. So it's now about 10 to 20 times faster in order to collect a spectrum relative to the previous measurements, and shown here is an example on one sample. So while we're doing this faster measurement, we still have the same high quality AFM-IR data in which it shows all of the known FTIR absorption bands that we have, showing not only dominant absorption peaks but also some of the minor peaks and side bands and so on. So it does give you the same high quality spectra that matches well to FTIR data and covers over a broader range, can give you very high spectral resolution as well as spatial resolution, and because it's using the resonance enhanced mode, has the capability to make measurements on very thin samples, even down to a nanometer thick if it's on the right substrate. So with that, we'll start off by going into a little bit of a background in terms of, just wanted to mention the benefits of nanoscale infrared spectroscopy as we see them. Essentially, the technique gives you the capability to perform nanoscale chemical analysis to really truly understand the chemical variation across the surface of your sample. And it does this using IR spectroscopy such that you have rich interpretable spectra. And then in addition to the point spectra that you can measure, you also have the capability to map out across the surface of the sample and do chemical composition imaging, or in the case of scattering SNOM, optical property imaging across the surface of your sample, and has sensitivity down to single monolayers. And all of this capability is demonstrated by the large and growing number of publications that have been put out by our customers. So we are excited to see this ever-increasing list of publications. So ANSYS Instruments, our company started initially doing a technique called nano-TA, which I'll describe in a little bit more detail. It's essentially a nanoscale thermal analysis measurement. We then extended our technology into mechanical spectroscopy, chemical information, and optical property measurements. So really our company is about taking scanning probe microscopy, using the nanoscale spatial resolution of that technique, but extending that spatial resolution in other modalities such as thermal or mechanical or chemical measurements. all at the nanoscale to provide you with a broad range of information about your sample. We're the world leader in nanoscale IR spectroscopy. We have a number of different products that you can see here, starting with the Nano IR system, which we introduced in 2011, the Nano IR2 a couple of years later, and just last year the Nano IR2S, which added the scattering SNOM capability onto our platform. We have a broad range of installed systems across the world and through a different institutions, government and academic and industrial. And through this we've been protective of our IP in terms of a number of different patents, and also we have demonstrating the innovation that we have with our different technologies, and we've also been given a number of different awards by R&D and a number of other bodies in terms of acknowledging the diverse capability and new capability of our system. So the Nano IR2S, I just want to mention, this system has these two complementary techniques. So it's one platform that you can get in which you can have either the AFM-IR technique, it directly measures absorption of the sample, and because of that gives you a highly interpretable spectra. And in addition, on the same system, you can perform the scattering SNOM technique. The scattering SNOM technique is, as opposed to AFM-IR, where you're using the tip as the detector of the absorption, in scattering SNOM, you're collecting in the far field the scattered light from the apex of the tip. And because of this and the properties of the scattered light, it's analogous to IR ellipsometry. And so it does a great job at mapping out the complex optical properties of samples, giving you very high spatial resolution, sub 20 nanometer spatial resolution, and excels in materials such as inorganics, 2D materials, and so on, materials that have good reflectivity. And so really these are complementary techniques providing somewhat different information and working on, best on kind of complementary samples. So really the combination of these two techniques gives you a very high performance system. So now we're going to describe a little bit the AFM-based IR spectroscopy, AFM-IR, for those of you who have not heard about this technique before. This technique was developed by a gentleman named Alexander Dawsey a number of years ago now. In 2014, he was awarded the Ernst Abbe Award for the invention of this technique. And essentially what happens is we have an AFM in which the tip is in contact with the surface of the sample. We have a pulse tunable infrared source, and the light of that tunable infrared source is directed at the probe location. We pulse the source. This causes some heating and expansion, which then induces an oscillation in the AFM cantilever, and it's shown here, this resonant oscillation of the AFM cantilever. And by looking at this cantilever oscillation amplitude, this is directly proportional to the IR absorption coefficient. So by taking this pulsed tunable infrared source and shifting the wavelength of the infrared source, we can map out a spectrum at a fixed location on a surface. And what's great about this technique is that it has very good correlation to FTIR. Here's a few examples in which we're showing AFM-IR data overlapped with FTIR data. And what we see is we don't see peak shifts, which can be induced by some techniques. And we see the relative strength of the absorption band is very similar. The peak width matches and all that kind of thing. And so the benefit of that is we can take the AFM-IR spectra and we can import those spectra into an FTIR database, a traditional FTIR database, and by using that IR database, identify materials that are unknown materials. And so this is a very powerful technique that has added on to scanning probe microscopy the capability to take an unknown sample and actually identify it chemically. So we're going to go through and show AFMIR animation. So essentially the system has incorporated into it an optical microscope, and we can use the optical microscope to select some location to bring the AFM probe down on, and then image the surface of the sample with the AFM. Within that image, we can then select a location by clicking on the location, which will drive the AFM probe there. And then what we do is pulse the infrared source, and this induces the resonant oscillation of the AFM cantilever. And we monitor that resonant oscillation using the traditional beam deflection technique of the AFM. And that resonant motion is induced by the infrared light impinging on the sample, causing the molecules within the sample, if the wavelength of the light is at the correct absorption band of the sample will absorb the light, expand, and cause the AFM cantilever to oscillate. And so again, here's showing the pulsing of the light, causing the AFM cantilever to oscillate and then dampen out. And we then shift the IR source over a range and get a local absorption spectrum. So this is how the traditional AFM-IR technique was performed, and it allows you to do AFM images, select a number of different locations on the sample, and collect chemical information across the surface of the sample. So the typical workflow that you would perform an experiment is, loading the sample again, collecting an AFM image, selecting locations either manually or programmatically. The system can then automatically acquire spectra, and using those spectra you can identify key peaks, which then you can acquire absorption images of those peaks, and by ratioing those absorption images you can make composition maps. So you have both composition maps as well as spectra on the surface of the sample. In addition to chemical information, the system also has the capability to make mechanical property measurements because of how the tip oscillates. Effectively, the sample is a spring in concert with the spring of the AFM cantilever, and by looking at the contact resonance of the AFM cantilever, we can determine whether a material is softer or stiffer and use that to map out across the surface, much like contact resonance AFM technique, which has been around for a while within the AFM community. So a few years ago, there was a technique which was developed called resonance-enhanced AFM-IR. And as opposed to the conventional AFM-IR in which you pulse and the tip oscillation damps down, in the resonance-enhanced mode, we're pulsing the light at each oscillation of the cantilever. And so we take the source, the IR source, which is typically a quantum cascade laser, and we vary its repetition rate to match the contact resonance of the cantilever. This creates a continuous oscillation of the cantilever and allows you to have improved sensitivity with measurements down to single monolayers. And what we've done now is develop the capability to do that same measurement much faster than previous and over a broader spectral range. So here we'll show fast spectra video. So this is essentially a spectra collected on one sample using the QCL source. We're covering a range of 1200 to 1800 inverse centimeters, so 600 inverse centimeters at a spectral resolution of 2 inverse centimeters. So still very high spectral resolution with this measurement. And it shows the high quality AFM-IR spectra, which took about 15 seconds in comparison with 1 to 4 minutes per spectrum with the previous AFM-IR technology. And here's a couple of examples of these measurements. This is some examples here on a polyether sulfone sample showing the measurements mapping out across the surface of the sample, collecting the AFM images and tapping and selecting regions, and we can then identify all these absorption bands and do spectral assignments of these absorption bands so we have a clear understanding chemically what is varying across the surface. And another application example here is on a reverse osmosis membrane. So this example shows the chemical heterogeneity within this reverse osmosis membrane. We can see this both within the spectra here, looking at the amide-1 absorption band and the variation of that relative to some of the CH bend modes. And we can also map that out by collecting an image focused on this 1660 amide-1 absorption band. So I mentioned that new nano-IR2S adds the capability of having an extended range for the resonance-enhanced AFM-IR. So the previous resonance-enhanced technique made use of quantum cascade lasers, which cover a broad range of the mid-IR, but do not typically extend up to this range, the 2700 to 3600 range. So we have a new exclusive source which we can make use of, and covering this range continuously from 2700 to 3500, which gives us the capability to look at the OH, the NH stretch, and the CH stretch in the resonance enhanced mode, so we get the capability to measure thin samples with high spatial resolution. And so now I'm going to move on and talk very briefly about some complementary measurements that we can perform using the nano-IR2 system, nano-IR2FS. So we have had the capability to perform nanothermal analysis. Essentially what we do here is we use a special modified AFM cantilever in which we can flow current down the cantilever to locally heat up the cantilever, the apex of the tip, and the surface of the sample. And by doing this, as we ramp the temperature of the tip, we can monitor the deflection of the cantilever, and we can determine the softening point of the sample locally where the tip is in contact with the sample. And then we can move the tip across the surface and collect a range of different nano-TA measurements. In addition, we can also collect an array and do something called transition temperature mapping, in which we can make a map across the surface of the variation in transition temperature. We can also make use of this probe to do a technique called Lorentz contact resonance. So this technique, we use this same thermal probe. We flow current through the thermal probe in the presence of a magnetic field, and this causes, due to Lorentz force, an induced force at the end of the cantilever, which allows us to monitor the contact resonance of the AFM cantilever, and we can probe that as we scan across the surface of the sample. And what's great about the contact resonance technique is by looking at different contact resonance modes of the AFM cantilever, we can not only measure samples which are soft, such as polymer samples, and this example here is a polymer sample, but we can also shift to higher resonance modes of the cantilever and look at much stiffer materials like this copper, tandem nitride, and ILD material of a semiconductor device. I mentioned earlier about the complementary technique of scattering SNOM. So essentially what we do in scattering SNOM is we again illuminate the probe and sample using a source, and this source can be in the IR or even in the visible as well. People have demonstrated into the terahertz. We then collect the scattered light from the apex of the probe, and by doing some techniques in terms of looking at higher harmonics of the cantilever oscillation and using an interferometer, we can differentiate the amplitude and phase of the scattered light, and we can make use of that to map out across the surface, both by doing images on samples or by varying the illumination in terms of the wavelength and mapping out phase and amplitude to look at essentially absorption and reflectivity of a sample. And so these are a number of different application examples showing nanophotonics, 2D materials, and the system can be used in the life sciences and polymers area as well, if that's the best technique for that specific application. And you can learn more information about the scattering SNOM technique by going to our website and looking at the webinars section. We have specific webinars which talk in more detail about scattering SNOM. So the system that we use to do the AFM-IR and scattering SNOM technique is a full-featured AFM. It has all of the traditional techniques used in AFM in terms of tapping and phase and so on. This shows a number of different modes that SPMs are used in. There's a whole host of acronyms that have been developed over the years in which you can take an AFM, operate in that mode to generate new information about your sample. Some of the newer techniques that we've more recently added onto the system is the capability to do fluid AFM, and so this shows an image here and shows the fluid cell on the system. This image shown over to the right here is looking down at the fluid cell where you can mount the probe onto the system, and then this is it in action in which we're making measurements and showing a fluid tapping image collected on a monolayer sample. So if you'd like to do AFM measurements in fluid, then this is an accessory for the system. And then the system has interchangeable application modules. So in this upper right image, what we can see is a nano-IR2 system. And the nano-IR2 system has installed on it here the nano-TA application module. This application module can be exchanged with a few different. We have shown here a CAFM module and a KPFM module. I'll explain briefly what those two techniques are. But this gives you more capability in terms of modes that you can operate on. Another thing about this system is this shows a dual source nano-IR2 system. So this box here is a laser switch allowing you to choose between, in this case, a quantum cascade laser and an OPO laser for making your AFM-IR measurements. So the Kelvin probe technique, this technique operates essentially in the tapping mode. So we have a tip, it's tapping across the surface of the sample. We use what's called a two-pass or a lift mode technique in which we tap along the surface and generate an AFM image showing the height of the surface of the sample. And then in the second pass, we scan the tip across the surface applying an AC plus a DC voltage, which is the output of a lock-in amplifier and a feedback loop. And what we're doing with this is we are shifting the DC voltage such that we get a null oscillation at the oscillation frequency of the cantilever. So by shifting around the DC voltage, we shift the AC oscillation of the probe from omega to 2 omega, effectively zeroing out the oscillation in omega. And whatever voltage is required to do that then gets plotted as what's called a surface potential image. This essentially allows you to map out work function and surface charges across the surface of the sample at the nanoscale. And these images here show an example on a nanocomposite sample. This sample is composed of graphene oxide and a polymer. We can see the topography of the surface in the height image, and within the phase image we can see some variations around the surface in which the stiffness varies across the surface. But the KPFM really highlights some of these domains within the sample in which there is a higher concentration of this graphene oxide relative to the polymeric material and a more evenly distributed region here. And the final application module that I'll talk about is something called conductive atomic force microscopy. This technique is again a technique in which we scan with AFM. In this case, we're doing it in the contact mode, scanning the tip across the surface of the sample. We apply a bias voltage to the sample. We use a conductive probe with a high gain current amplifier to then make a conductivity image. And so typically you're looking at picoamps to nanoamps of current flow between the sample and the tip, and map out, in this case, variation in the concentration of a conductive polymer relative to a non-conductive polymer within this sample. And so with that, I would like to turn the presentation over to Craig, our CTO, and he is going to cover some new publications and applications with the system.
All right, thank you very much, Kevin, and thank you everybody for staying and listening to the second half of the presentation. I want to hit on three main points related to new publications and applications. And one is there's an exciting new publication out of CIAC and Exxon demonstrating the ability to do quantitative measurements of concentration with AFM-IR. And so I'll talk about that. And then I'm going to survey a number of other life sciences and material sciences applications that have been published recently. So you may have already got a sense of this from Kevin's part of the presentation that there are a very large number of applications for nanoscale infrared spectroscopy, and I'll talk about some of these, but lots of applications in material science and life sciences covering both academic research and industrial problem solving. So I'll be talking about, as I said, applications in both material science and life sciences. So first of all, let me give you a tour of a few things on our website that may be useful resources for you. On our website, we have a publications tab. So if you're interested in any of the topics that we're talking about today that have been published, there'll be a little publication icon on the slide. If you go to our website, it will have a link to those articles, and there's a very large and growing number of articles. There are other resources on the website, including product and technology information, and as Kevin mentioned earlier, a number of webinars. And let's just give you a tour of a few of these that are previously recorded. We had a wonderful webinar by Greg Myers, who talked about nanoscale IR spectroscopy on polymer systems from an industrial perspective. One that Kevin mentioned, focusing on the SNOM technology, a great presentation by John Raybolt on single nanofibers, and I'll talk a little bit about that. An excellent presentation by Simone Ruggieri on protein misfolding and using AFM-IR to characterize early stages of neurodegenerative diseases, and a variety of other webinars, including one by Kurt Marcotte on polymer problem solving, Andrea Centroni on applications to perovskite solar cells. And I'll touch on some of these, but if you're interested, I encourage you to go and listen to these webinars for more details. So I mentioned this exciting new publication about quantifying chemical content in polymer blends with AFM-IR. So this was a paper published recently in Analytical Chemistry, a collaboration between the Chengchun Institute of Applied Chemistry in China and collaborators at Exxon. And what they were looking at was a polymer blend of high-impact polypropylene. And you can see an AFM phase image of this sample in the left here. And this sample has a structure where there is a matrix material, and then these phase segregated regions which have both an intermediate layer that's distinct from a matrix and then a core that is distinct from the intermediate layer. And then there were open questions about what is the chemical composition of the different locations within these nanodomains. So what this team did is they used a combination of AFM-IR and then conventional bulk infrared spectroscopy, FTIR, to build up a calibration to perform this quantitation. So the first thing that they demonstrated, and that we've shown in our webinars, is that there can be very good correlation between measurements made by FTIR, in this case shown in the dark color, and AFM-IR shown in the reddish pink color. And so once you know that there's a good correlation, you can use what you learned from FTIR to inform measurements by AFM-IR. And in specific, they looked at pure materials of polyethylene and polypropylene and noted the characteristic peaks associated with, for example, polypropylene and the polyethylene. And then what the team did is they used reference samples of known concentration, and they examined them by FTIR, and they made a calibration curve looking at the ratio of this peak height to this peak height, and were able to basically establish that there was a linear relationship between the ratio of those peak heights and the concentration in the polyethylene versus the polypropylene. So now, how do we apply this to locally quantitate material concentration in AFMIR? Well, what they did is they took a series of spectra at different locations on a sample, and this is showing a topography, sort of a close-up of one of the nanodomains, and then an AFMIR absorption image taken at this 1378 peak, and you can see some variation in that polypropylene content. But if they then normalize to this 1378 peak and then look at the variation in the 1456, or the ratio of those two, they can go back to this calibration curve, from that ratio, read off the concentration. And so what they were able to do is determine that in the matrix and in the intermediate layer and the core, there were different concentrations of the polyethylene content. And so they were able to specifically quantify and identify the distribution of the concentration of these components in the polymer blend. Now I'm actually going to jump back and forth between life sciences and material science. So this is a life sciences application. This is a really interesting application on the cell biology. So these are measurements of breast cancer cells, an AFM topography image in the upper left, and then there are 3 absorption images here done at different absorption bands. So this one here is tuned to the amide band, which shows the concentration of protein. This one here at 1090 inverse centimeters corresponds to the DNA and RNA, and so highlights mostly in the nucleus. And then this team in France, they developed a novel molecular tag based on a heavy metal carbonyl, or excuse me, a heavy metal tag that they were able to put at a location in the spectra where there are not typical absorptions in biology, and so they can tag to specific molecular targets. And then another application, this one is really fascinating. This is a research group in France, and what they were looking at was parchment, including pieces from a 15th century map. And the question that they were looking at is, could they investigate degradation of this parchment material using AFMIR? And it's known that parchment, which starts out primarily as collagen, over time it degrades, it gelatinizes, into a gelatin. And so they started out by looking at pure samples of collagen and pure samples of gelatin, and they could see the characteristic peaks. For example, there's a characteristic peak at 1724 that shows up in the gelatin that is not present in the collagen. So these are the control samples. Now they went to degraded parchment samples, either intentionally degraded or this natural map sample, and they acquired spectra at different locations, and they could see that some of the locations showed very small amounts of this 1724 peak, showing a very small amount of degradation, and other regions that were highly degraded. And so then they could tune the IR laser to the absorption band associated with this gelatin, and then make a map showing the most highly degraded regions. Another application that's really exciting is looking at organic nanocontaminants. So if you use a cell phone or a computer, you are using materials that are made from silicon wafers, high-speed electronics that have very, very fine features. And in the production of these electronics, if you have particles or dust on the sample, it can compromise the performance of the device or make it such that it doesn't even work. So the semiconductor and data storage industry and optical display industries are very heavily focused on identifying the sources of contamination on their substrates. And typically what they can see is, well, they see a blob, but they don't necessarily know what it is. What we're able to do with the AFMIR is go in and look at a very small defect and take absorption spectra that can let us unambiguously identify the source of that contaminant. This is an example where you can see what looks like, maybe just one defect, but when we look at the two different regions of it, we can see that one of them has amide bands, so that we know it's of a biological origin, and in this case skin. And then from the spectrum of the blob down below, when we compare that to a reference spectrum, we can identify that that's polyester, for example, from a polyester fabric. There's also been a lot of recent work on conducting polymers, and AFMIR has been used to look at conducting polymer nanostructures. These are examples from two different publications of radiation synthesized conducting polymers. In the top example, it's photosynthesized PDDB, and by looking at the amplitudes of some of these peaks, they can measure the degree of polymerization in these little nanostructures. The example down below is electron beam irradiated. It's irradiated in the presence of this K2SO8 material, and there is so they're able to look at these nanostructures and determine the regions that have high concentration of this K2SO8 and regions where you have more complete polymerization of the P dot. Another application in the life sciences, Andrei Kulik and Simone Ruggieri and collaborators at EPFL, and now Simone is at Cambridge, have been working on looking at protein secondary structure. Basically, this is an example of collagen fibers, where you can look at the topography, the IR absorption, even the local stiffness. But if you look at the amide 1 band, the shape of the amide 1 band can give you information about the protein secondary structure. The fraction of beta turn and alpha helix, random coil, etc., can be quantitatively determined by the shape of that peak. And so the team at EPFL and now Cambridge has been looking at protein misfolding at early stages of neurodegenerative diseases. And for example, looking at the degree of protein misfolding in oligomers and nanofibrils. Basically, by looking at the shape of those peaks, they can see the degree of misfolding at what stage in the protein aggregation and amyloid formation process. Another example, this one from the US, Bharat Bhushan's group, have been looking at nanoparticle composites, where the nanoparticles have been engineered to have re-entrant geometries that controls the wetting between the solvent and these nanoparticles. And as a result of that, they can control the amount, or they can at least impact the amount of crystallinity in the polymer. And so by using AFMIR and looking at the spectra, they can get indications of the degree of crystallinity in these nanocomposites. A really nice example, and we have a whole webinar on this, as I mentioned earlier, by John Raybald, is electrospun polymer nanofibers. And what they were able to discover is looking at these small nanofibers, that these fibers form a core shell structure that have two different phases, a crystalline phase and an amorphous phase, and that these two phases have slightly different peak positions for the carbonyl band, 1728 versus 1740. And so then if they map if they tune to one peak or the other, they can map the distribution of these two different phases, and we're able to demonstrate that they had a high concentration of the amorphous phase in a very thin shell on the surface, and then a higher concentration of the crystalline phase on the interior. Another example that I am very fond of is this measurement involving failure analysis of a polyurethane tubing. So this polyurethane tubing was degraded to the point that it cracked, and what the researchers were able to do is take spectra in the sort of unaffected region away from the crack, and then compare that to spectra right along the crack, and they could see the appearance of certain bands, increase in certain bands right along the crack, and able to identify that these peaks were associated with specific bond scission, and basically identify the specific mode of the failure in this material. Another really exciting application, and we have a webinar by Andrea Centroni recorded on this, is looking at perovskite materials. I'll just show one quick example. This is a measurement on this perovskite material that has been, there's been a bias applied across the material. And so if you look at the 1468 peak, which is associated with a methylammonium ion, with no bias, it's relatively uniformly distributed across the material. But once you apply a bias of 80 volts for 100 or 200 seconds, you can see how this methylammonium ion migrates and increases the concentration towards the cathode. So really interesting images there. And then I think this is the last example I wanted to show. This is a really interesting where treated with cycles of exposure to vapor at different temperatures, different number of cycles, and then the researchers have been looking at the depth of penetration of the treating chemical into the core of the fiber based on the amplitude of peaks that are associated with the the specific treatment chemical. So you can quantitatively see the depth of penetration for different process parameters. So with that, I'd like to wrap up, and it's traditional at the end of a presentation to show a conclusion with some bullets about what we talked about. But I thought today I would do things a little bit differently and let our customers speak for us. So we've been very, very gratified to see the amazing discoveries that our customers and collaborators have been able to make using our AFMIR, NanoIR 2 and 2S products. And so I hope you have enjoyed this webinar. And at this point, we would like to invite your questions.
All right. Well, great, Craig. Thanks for going over those applications. So I'm going to cover a question. A question was asked about the new laser source, the source that covers the 2700 to 3600 range. Does that allow selection of any repetition rate like the quantum cascade laser, or is it a coarser repetition rate? So the new source can be tuned over a range. The repetition rate range is not as broad as the QCL, but the range does cover a number of different contact resonances for both the contact style AFMIR probes and the tapping style probes. So it isn't a course in which you have to step. You can actually sweep over some range and match the repetition rate to the contact resonance of the cantilever, giving you the enhancement that allows you the improved sensitivity.
Okay, we have a question, another question about the laser source. I'm not sure I understand this question, so if I answered incorrectly, feel free to ask a follow-up question. But I think this is a question about the new source for resonance enhanced that covers the CH, NH, and OH, and question is it also a QCL? How many chips? No, it's based on a different technology, and so it's a a single crystal technology that tunes over that full range.
All right, and then we have a question about can we make IR spectra in liquid? So the answer at this point in time is no. We are headed that direction. Part of introducing a fluid cell to our system is to work on expanding the capability of doing IR spectra in fluid, and so there is some development work that's ongoing at a number of different research groups as well as some at ANSYS, in which we would like to get to the point of having AFM-IR in liquid, but that's currently not a capability that we offer.
Yeah, just to add to that, there is one publication by the DASI group in France where they demonstrated some AFM-IR measurements in liquid. The main challenge associated with doing AFM-IR in liquid is that the liquid adds a very large viscous damping force onto the cantilever, so it makes the detection of the IR absorption not as efficient as in air. But as Kevin said, it's something that we're very interested in and we'll continue to work on.
Okay, so there's a question about how to prepare polymeric and biologic samples for AFM-IR. So the AFM-IR technique works best on thinner samples. So, effectively, using the resonance enhance, we can measure samples if they're on the right substrate down to as thin as 1 nanometer. If they're on arbitrary substrates, 10 or 20 nanometers. So really, the answer in terms of measuring polymer or biological samples is getting a sample which is thin. Now, typically, that's reasonably straightforward with a biological sample. If it's a collagen fiber, you just deposit it onto a substrate, and the fiber in and of itself is thin. Or if it's a bacterial membrane, again, the exact same thing. So the challenge is more typically in if you're looking at like a tissue sample, then a tissue sample would need to be sectioned and deposited onto a substrate. And if you're looking at a bulk polymer sample, we look at lots of polymer samples which are just deposited as thin film, or they're spun down onto a surface or drop cast. But if you have a bulk sample, then again, that would best be prepared using a microtome or a cryomicrotome, depending upon the temperature, transition temperature of the sample.
Okay, we had a question that said, could we comment more on the resolution of the technique? Is there a convolution between the sample and the tip? So this question is about spatial resolution, and the spatial resolution is limited by one of two things. In especially the previous technique, before the resonance enhanced technique, the spatial resolution could be limited by thermal diffusion, basically the spreading of heat from the point where the IR light was absorbed. With the resonance enhanced technique, we use a metal coated tip that locally enhances the strength of the E field from the infrared light, and so in that case we can get spatial resolution that approaches the tip radius. It depends a little bit on the sample and exactly what mode that you're operating in, but the best spatial resolution can be a few tens of nanometers with the tip radius.
There was a question, is there a source that covers the 2250 inverse centimeter range? So we have for a while supplied a source, an OPO source that covers from 900 to 3600. So the traditional AFM-IR technique does cover that range because it covers the full range from 900 to 3600. In addition, if you're looking at a sample which is thinner and you need the increased sensitivity of the resonance enhanced technique, then quantum cascades are made with a range of different center wavelengths. And so typically for the quantum cascade laser, we use quantum cascade lasers that cover a range from 1,000 to 1,800s. And typically that will require 4 QCLs. Each individual QCL chip covers a narrower range, but we'll use 4 of them together to cover that 1,000 to 1,800. And they do have quantum cascade chips in which they center more at the 2250. And so that would be another option besides the traditional OPO for AFMIR if you're interested in covering that range.
We had another related question about why is a region above 3,600 inverse centimeters not accessible? And actually, both of the lasers that we have in the CH range, both the new resonance enhanced one and our older one, they actually tune out to 4,000 inverse centimeters or 2.5 microns. There are typically not a lot of absorption bands, above 3,600, so we typically limit it to 3,600. But if there is an application where you need to get out to 4,000, you can certainly talk to us about it.
So there's a number of questions about how can IR determine the crystallinity of a material. And so essentially what happens is whether, this is not true of all different polymers, but certain polymers, whether a material is more or less crystalline can impact the strength of absorption bands related to that specific bond of the molecule. In addition, the system that we have has the capability to have an optional polarization rotator in which we can rotate the polarization of the incident light and see effects, in relationship. Do we have the incident light oriented with respect to a molecular bond or oriented away from that molecular bond? So by combining those two things, then there is the capability to look at peak ratios between the different absorption bands and characterize whether a material is more highly crystalline or more amorphous.
We have a nice comment from one of our participants today, Andrei Kulik, who also was a co-author on some of the research that I mentioned today in response to the resolution question, where he says we had 10 nanometer on the inhomogeneous LHCII samples. So those are some specific resolution measurements on some real-world samples where they achieve 10 nanometer spatial resolution.
So there's a question about the new source and would this source be compatible with scattering SNOM? So typically scattering SNOM requires either a CW or what's called a quasi-CW, which means a very high repetition rate source, because essentially what you're looking at is the scattered light from the apex of the tip. And you want to see that interaction between the tip and sample throughout the entire oscillation of the tip cycle. The tip is tapping, and so moving vertically away from the surface of the sample and returning to the sample, and you want to really interrogate the scattered light throughout that motion. So having a lower repetition rate source would be a challenge for scattering SNOM and typically not used. You need either a quasi-CW, a high repetition rate, or a CW source for scattering SNOM measurements.
There's a question about what happens if the IR laser interacts with the tip. Does it affect the measurements? Our original nano-IR specifically tried to avoid this issue by using illumination from below. We mounted samples on a IR transparent prism and used total internal reflection illumination to minimize the light impact on the tip. For the nano-IR2 and the nano-IR2S, we use topside illumination where some light does in fact impinge on the tip, and if you weren't careful about it, it could potentially cause some issues. And so that was something that we worked on and developed specific probes that minimize the interaction between the IR laser and the tip, so that we can get good spectra even if some light hits the tip.
There is a question about what is the limitation on probe choices for the techniques. And so for both AFMIR and scattering SNOM, then it's beneficial to have local enhancement at the apex of the tip. And so really what that means is it means, you know, you need free electrons at the apex of the tip. And so effectively that means a metal coating or some type of very conductive coating at the apex of the tip. So for both scattering SNOM and AFMIR, typically we're using probes which are coated with gold or coated with platinum or platinum iridium, things like that. And so that gives you this local enhancement at the apex of the tip. Now, a fortunate thing in relation, you know, there's alternate technology called TERS, which gives you high spatial resolution Raman spectroscopy. Within the TERS technique, then it's more challenging to get the Raman enhancement off of the tip. And also, in order to get the Raman enhancement, typically it's a short-lived, you know, phenomenon in which the tip needs to be very freshly prepared. So in relationship to TERS, then AFMIR is much simpler. The probes that we supply, you know, work well, and we expect, you know, all the probes to generate some enhancement and some AFMIR signal to give you, you know, the spatial resolution of the technique. So in that sense, there's not significant limitations on the probe choice, and the probes are readily available.
We have a question that says, in SNOM, IR or the peak IR position shifts with changing sample thickness. Do you observe that? So yes, the questioner is correct that in SNOM, because it's a scattering process, the IR peak absorption or peak scattering positions can shift with both sample thickness and substrate and material. This has been very nicely quantified by a paper from the Hillenbrand group. In AFMIR, we do not observe that. And the reason is that in AFMIR, we're directly measuring the absorption of light, not the scatter of light. And that absorption of light is, you know, it follows the same fundamental measurement as conventional FTIR. So we don't see peak shifts. And because of that, we can do certain types of measurements. For example, I showed the nanofibers, the electrospun nanofibers, where we could distinguish you know, the crystalline and amorphous phases of that material on the basis of those, you know, real absorption peak shifts.
There is a question on, can we measure in the same position using nano-TA, LCR, and nano-IR? And so the answer to that question is that the nano-TA and LCR techniques require the use of these thermal probes, special thermal probes called thermoleader probes, in which you can flow current down the probe in order to locally heat or induce this force required for LCR. And those probes are typically not used for nano-IR. They don't have a metallic coating, as I mentioned, that's useful for the nano-IR technique. And so those measurements would need to be done. The nano-TA and LCR could be done using the same probe in the same location, but then you'd need to exchange the probe and go back to the same location in order to make nano-IR measurements. And we have, and a number of our customers have done, you know, multiple modes to measure both chemical information, but also mechanical information and thermal information as well at the same locations on the surface of a sample.
Okay, let's see, we had a question about samples with a hard surface with a liquid lubricant on them and how will the tip be affected by the liquid. It sort of comes down to how thick the liquid is. If it's a thick layer of liquid, there is the potential that the AFM tip will be affected by the liquid, and if we're doing like a tapping type measurement, it could get stuck. If it's a very thin liquid, especially a more viscous liquid, then it can be possible to image some of those samples.
There's a question about would it be possible to perform AFM-IR analysis in controlled atmospheric conditions. The system is enclosed, and we do that for the primary reason because we recommend that the system be filled with dry air or dry nitrogen. Water vapor in the air absorbs within this region of the mid-IR, and so you get better spectra, better measurements if the system is purged using either dry air or dry nitrogen. Because it is enclosed, then you could exchange that gas with something else and perform measurements as long as the gas is inert, not hazardous gas or things like that.
And then we're certainly interested to hear about specific applications like that in terms of the experiments that you want to do to help inform how we extend the capabilities of the instruments going forward. There's a question about is it possible to get quantitative mechanical analysis to get the modulus from the contact resonance frequency measured. So a couple things I wanted to mention on that. One is just to remind people that there are two ways to get those mechanical property measurements. One from the contact resonance in the AFM-IR measurements, and then separately from that Lorentz contact resonance. And in principle, it's possible to quantify mechanical properties from the contact resonance, and there have been a number of publications, for example, from the NIST group, and there's a nice webinar recorded at our website by Donna Hurley, who talks about some of the quantification efforts. In practice, this is a bit challenging because there are a lot of parameters that influence the conversion between contact resonance into elastic modulus. So in practice, most people do relative measurements rather than absolute quantitative measurements with the contact resonance. All right, there are a few more questions about things like upgrades and costs associated with that. We'll get in touch with you individually to discuss those. And there are a few other questions that we're out of time to answer right now, but we'll get back to you individually to discuss those issues, or those questions rather. So with that, we'd like to thank you very, very much for your participation today, especially all of your questions, and we look forward to seeing you either in person at an upcoming conference or joining you for another webinar in the future. Thank you so much.
Thank you. Have a good day.